So this is a video lesson on 6.4 sum and difference formulas, chapter 6, section 4. We're going to talk about sum and difference formulas and how we can apply those into different types of problems. So the first two we're going to look at are the sine functions in terms of sum and difference. Here, the sum formula, if I have a sum of two different angles, that's going to be the sum of sine and cosine of those different angles plus, because the signs are the same, and then cosine of the previous angle alpha times the sine of the previous angle beta, which was cosine earlier. Difference for sine function, same type of pattern, sine, cosine, sine, but with a minus minus. Cosine, however, in its functions, actually go ahead and follow. If cosine comes first, right, if you think of the cosine of the sum, then the cosines are going to come first, and then it's a difference. So sum changes to difference, and then sine and sine. Cosine with a difference actually becomes a plus, and then it's cosine, cosine, sine, sine. So if you can kind of follow that pattern, you can see how the sum and difference formulas work. Also tangent, sum and difference, where these come from, you could verify them using kind of the ratio of sine of a sum over sine of a cosine of a sum. But other than just coming up with that formula, we can always just kind of just remember those. Remember, this is kind of like the sine of a sum over the cosine of a sum. And same thing would be for difference. But again, we can kind of verify those, or you can kind of just go ahead and memorize this type of formula and kind of see that the plus in the angles here falls with the plus up in the numerator, and then obviously minus in the bottom with the product. Here, if I have a minus, then this is a minus, and this is going to be an opposite sign plus. Just got to remember that one in there as well. So when we're using these formulas for sum and difference, we want to make sure that we take our formulas, and we're going to usually find the sine, cosine, or tangent of an angle that's not on my unit circle. So what I want to do is I want to go ahead and take this 75, and I'm going to rewrite it in terms of maybe a 30, 45, or 60 degree angle. We like to use those angles in the first quadrant, just because we know those values really well and we can plug those in quickly. When I'm looking at the sine of 75, then I want to take the sine of the sum of two angles, for example 30 and 45. If I take the sum of those, or 45 and 30, 45 and 30 add up to 75. However, also, since I have my sum formula, I can break this down into two parts. I can break it down into the sine of 45 degrees times the cosine of 30 degrees. I'm just using my sum formula for sine, plus the cosine of 45 degrees and the sine of 30 degrees. And again, once I have those broken down, then I can go ahead and just kind of find their function values. So sine of 45, I know that's root 2 over 2. Cosine is root 3 over 2 at 30 degrees. Plus cosine of 45, that's root 2 over 2, times the sine of 30 degrees, which is 1/2. And again, from there, just simplifying, I'm going to go ahead and just kind of multiply here and get the square root of 6 over 4, square root of 6 over 4, plus square root of 2 over 4. So really I can kind of combine those and get the square root of 6 plus the square root of 2 all over 4. Example 2, use the formula for, now rather than degrees, I have something in radians. Pi over 12 is relatively small. It's smaller than my smallest possible value. And remember, we're looking at the first quadrant angle. So pi over 6, pi over 4, and pi over 3. However, it might be helpful to change these angles with respect to the denominator of the angle I have, 12. So here, pi over 6 is really like 2 pi over 12, sorry. This would be like 3 pi over 12, and this would be like 4 pi over 12. By just changing the denominator, I can easily find maybe a combination of these three angles, or two of the angles that would give me pi over 12. Rather than a sum, actually here I'm going to use a difference. So I'm going to look for the cosine of maybe the difference of 3 pi over 12 minus 2 pi over 12. And that gives me just a single pi over 12. remember, we changed these originally, so let's change it back so our unit circle values. 3 pi over 12 is really just pi over 4. And 2 pi over 12 is really just pi over 6. So again, let's go ahead and just kind of plug those values in. Remember our cosine difference formula. Cosines come first, so it's cosine of pi over 4 times the cosine of pi over 6. Minus is really going to be a sum when it comes to my formulas. I can check that from above. Sine of pi over 4. Need a little space here. I'm going to get rid of those right there. And then this is going to be the sine of pi over 6. And again, just to remember, I'm going to look for those values in my first quadrant. Pi over 4, that's over here at root 2 over 2, right? And pi over 6 is down here, and he's got a root 3 over 2 x value and a 1/2 y value. I'm sorry, pi over 6, yeah, that's like 30 degrees, so that should make sense. And then again, just go ahead and plug in those values. Cosine would have been root 2 over 2 times the cosine, which is the y, so that would be root 3 over 2 plus, here I have the sine of pi over 4, root 2 over 2, times the sine of pi over 6, which would be 1/2. And again, when I take that sum, I'm going to multiply. Remember, I can't multiply. I can multiply different radicals. So it's going to give pi over 6 over 4, and this is going to give me root 2 over 4. It's going to be a sum. So they're both over 4. I have root 6 plus a root 2. Okay. Go ahead and try the tangent function next. See if you can find that exact value. Remember, 7 pi over 12. You're going to try to pick two angles that can add or subtract to 7 pi over 12 and find that value. So if you want to pause the video and try that now, go ahead and do that. The two angles I would have picked probably would have been tangent of pi over 3 plus the tangent of pi over 4. When I add those up, this is really 4 pi over 12, and this is 3 pi over 12, which adds to 7 pi over 12. And then remember tangent, it's going to be the tangent of pi over 3 plus, same sign up top, tangent of pi over 4, and it's 1 minus, opposite sign, of the product of those two tangents, pi over 3 times tangent of pi over 4. Again, from here, it's just kind of just plug and chug. Look at your unit circle, find those tangent values, find those tangent values, and then just see where the problem takes you. So here, tangent of pi over 3, that's going to be root 3 over 2, or tangent, I'm sorry. Tangent, again, what I'm looking at is over here at pi over 3, which is up here, and I have a y value of root 3 over 2 over 1/2, so really that's just going to be root 3, plus tangent of pi over 4, that's the easy one, that's just 1, because it's x and y values are the same, so their quotient is going to be 1, minus tangent of pi over 3 already found, that was root 3, and then my tangent of pi over 4, that's going to be 1, I'm just going to multiply it by 1. Again, simplifying this isn't very hard, and we don't have to go very far either. We can just go ahead and leave this as square root of 3 plus 1 all over 1 minus the square root of 3. I could multiply by the conjugate to simplify that a little further and get maybe a monomial denominator. But at this point, with what we're trying to do, that's fine enough. Really, what I really want to work on is using the formula, and then plugging in values to find the exact value. Find the exact value of this one. Now here we're actually going backwards, so we're using one of our sum or difference formulas, and we need to go back and see what it would be. Because typically when they give you something like this and these angles do not belong to your unit circle, usually if I take the sum or difference, they will belong to my unit circle. So if you want, you can peek back up at your top of your notes and kind of compare and contrast. Here I have sine, cosine, or cosine, sine. So that tells me that different trig functions being multiplied, so it's most likely the sine of something. And then since this is a difference for sine, it's going to be a difference down here. So I have the difference of 20 and 80 specifically. So when I look at this, it's actually going to be 20 sine of 20 degrees minus 80 degrees. And that does give me a negative angle, so sine of negative 60 degrees. Which isn't a big deal. I just got to make sure I go in the right direction in terms of my function. Remember, when we use our even-odd properties as well, sine of a negative angle measure is equal to a negative sine of x. So here I can really set this equal to negative sine of 60 degrees. Sine of 60 degrees on my unit circle, sine is going to be root 3 over 2, so this is a negative root 3 over 2 for my answer. Let's go ahead and turn to the last page here. It's a real quick lesson, 6.4 in sum and difference. The first one is just applying the sum or difference formula. Pretty rote memorization. Here we have to do a little bit more of a application based and apply some things. So let's look at example 5 together before we move on. So they're giving me two different trig functions, cosine of alpha, and they're giving me sine of beta. They also tell me something specific about alpha and beta in terms of where they're located. And then they want me to do is they want me to find the cosine of their difference. They want me to find the cosine of their difference. So the first thing I want to look at is I want to take this first piece of information here, and I want to make sure that I understand that in terms of where that angle is located and find all of its different function values on its triangle. Because remember, cosine of an angle is a ratio, so this is telling me about the adjacent and hypotenuse sides of that right triangle that form by alpha, and then I might want to look at the same thing for beta. So here, when I look at this triangle, since alpha is between 0 and pi over 2, I know it has to be in the first quadrant. And then also, when I draw alpha in the first quadrant, I can label the adjacent side as root 5, and the hypotenuse is 5, and then that helps me try to figure out what the third side might be. Using Pythagorean theorem, if I square 5, that should be equal to the square root of 5 squared plus the third side. We'll call it b squared, or I should guess it is a y value, so we'll call it y squared. 25 equals 5 plus y squared. Subtract 5, 20 equals y squared, and then y would be the square root of 20. The square root of 20 can be simplified to 4 and 5, so that would be 2 radical 5. So 2 root 5. And then looking at sine of beta, let's look at that angle. That is also in the, well, negative pi over 2 to 0, so that obviously tells me I'm in the fourth quadrant. That's my beta angle right there at the origin. There's my right angle. They tell me the sine is opposite over hypotenuse, so this is negative 4 over 5. And 4 and 5 here obviously trigger you to use Pythagorean triple, so 3, 4, 5 would be my triangle here for beta. And now what I want to do is I want to go ahead and find the cosine of the difference of those two. So here I'm going to rewrite the cosine of alpha minus beta, and I'm going to remember my cosine difference formula, which is the cosine of alpha times the cosine of beta. Not minus, but plus the sign switch, sine of alpha, and sine of beta. So now all I have to do is look at my angles and my cosine values. So here sine and cosine of alpha are going to be, cosine respectively is, we know is root 5 over 5. And sine of alpha is 2 root 5 over 5. For cosine and sine of beta, cosine would be 3 over 5. And sine of beta would be, we know that as negative 4 over 5. we're going to take their sum, and the first thing we want to do is with the products, we want to multiply the denominators and the numerators. So I have 3 radical 5 over 15. Oh, sorry, 5 times 5 is 25. Plus 2 root 5 times negative 4, that's negative 8 root 5 all over 25. And when I take the difference of those like radicals, I end up with a negative 5 over times root 5 over 25, which, since 25 shares a common factor of 5, I can simplify this to negative root 5 over 5. So you kind of see how this problem kind of works. You start with the two individual angles, find their triangles, respective triangles in terms of alpha and beta, and then kind of use the sum or difference formulas to work to find those individual function values. Find the exact value of the sine of sine inverse minus tangent inverse. So here we're going to kind of go back to 6.1 and use some sine and sine inverses, but also 6.2. The first thing I want to remember here, when I'm taking a trig inverse, this is going back, trig inverse of a ratio, that's going to have an output of an angle. So I, in my head, can kind of realize that this sine inverse of 4/5 is really some angle. We'll call it alpha. And also, I could look at tangent inverse of 3 over 4, which that's another angle. We'll call it beta. We don't know if they're the same angle. We can't really tell at this point, so we'll just name them as two different angles. Then what I'm probably going to want to do is I'm going to have to figure out my missing sides, because if I'm trying to find the sine of the difference of two different angles, the difference of alpha minus beta, if I'm trying to find that difference, what I want to do is I want to go ahead and figure out the individual sine and cosine values of alpha and beta using my two triangles. And then that'll help me find my missing pieces. So here for alpha, sine inverse of 4 over 5, that's got to be in the first quadrant because sine's either in the first or fourth. Since it's positive, I know it's in the first. So this is alpha, and sine is opposite over hypotenuse. So the third side would be 3, using my Pythagorean triple. And then also tangent, if tangent's positive, I'm also in the first quadrant. So it's going to be opposite over adjacent, and that's going to also have a hypotenuse of 5. So they are two different triangles that we're looking at here. So we want to go ahead now and find the individual sine and cosine function values of the difference formula. So this is equal to sine of alpha times the cosine of beta minus sine stays the same, cosine of alpha times the sine of beta. And let's go ahead and just find those sine and cosine values for alpha. So that would be sine would be opposite over adjacent, opposite over hypotenuse, so that would be 4/5. Cosine would be adjacent over hypotenuse, that would be 3/5. And then for beta, cosine would be 4/5, and sine would be 3/5. When I take those products, I'm going to end up with, this is going to give me 16 25ths plus 9 25ths, which when I add those two fractions together, since they have like denominators, oh, sorry, someone made a mistake. Oh, see if I can catch it here. This is really a minus. So we'll take a subtract, take that. Excuse me. And I subtract here. So when I take that difference, I end up with a 7 over 25. That's my final answer. Number 7, we're almost there. We're going to establish identity. That's just that verifying process. So let's go ahead and go through that verifying process that we learned last class in 6.3. Here I'm taking the sum of cosine of two angles and the difference of cosine of two angles, and I want to say that that's equal to that. 2 times the cosine of alpha times the cosine of beta. When I'm verifying an identity, I probably want to pick the more complicated side and kind of go from there. So when I'm establishing identity, here I got more sums and differences on the left. Maybe I'd go ahead and try to simplify that. I just learned the sum and difference formulas for cosine, so maybe by starting on that side I'll kind of see something hatch itself out. Remember, cosine of alpha over beta, that's going to be the, we'll start way over here. I have the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. Now that I have that piece, we'll add that to the remaining cosine difference function. So this will be cosine of alpha. I'm running out of space, I'm going to try my best. Cosine of beta minus is going to be plus sine of alpha, sine of beta. If you have to run over a little bit, that's fine. Shouldn't be too much of an issue. Here, when I look at these four terms, I have a term right here, I have a term right here, a term right here, a term right here. I can recognize that the sine of alpha, sine of beta here is going to cancel out with a negative sine of alpha, sine of beta right here, very nicely. And all I'm left with is two of these cosine alphas, cosine beta. And when I look at that, I realize they're the same thing. This will be a helpful identity moving forward, especially when we start talking in 6.5 about the double and half angle formulas. Also, we have these cofunction identities. We kind of tucked this in at the end of the lesson. Don't be too freaked out here. When you're looking at a theta with a pi over 2 minus theta, remember pi over 2, what does pi over 2 represent? Well, pi over 2 is kind of like that 90-degree angle in degrees. So when I look at a right triangle, and we'll call this acute angle the theta, and that's my 90-degree angle, what would my other angle technically be? If I wanted to use it with respect to this angle being pi over 2 and this being theta. Well, the only way to name this angle is the other acute angle. So we got a pi over 2 and a theta angle. So when I look at to find the other acute angle, if this is the acute angle, this has to be the complementary of that. So if I take away theta from pi over 2, that will find my other angle measure right there. So, obviously, when I look for theta, this theta has an opposite side here, and it has an adjacent side here, and a hypotenuse here. But if I'm standing at this angle, pi over 2 minus theta, then the opposite side would be the adjacent side of theta. The adjacent side of this angle would be the opposite side of theta, and the hypotenuse stays the same. So since the O and A kind of switch for the corresponding sides, when I talk about the sine of the cofunction identity here, the cofunction angle, this angle for sine is opposite over hypotenuse, obviously, right? And then cosine would be from here, be adjacent over hypotenuse. And when I look at that, I go to the same side. So O and A, remember, they're kind of the same here for the two different angles. That makes these two function values the same. Same works for tangent, cotangent, same works for secant, cosecant, respectively. So go ahead now, once you've finished watching the video, rewatch if you have any questions, and then try the homework questions below. Not these from this video, obviously, but the ones that are on your sheet.